Hello everybody, my name is Sheena Mohan and I'm going to talk about the Gpio chip and drivers in Zephyr. Zephyr is a real-time operating system which provides a small footprint kernel designed for resource-constrained systems. It is mostly used for small and simple embedded applications. It has a monolithic kernel and provides all services. It has a common shared address space, so the application and the kernel use the same address space. This avoids the overhead of context switching. In Zephyr, all the system resources are to be defined statically at the compilation time. This reduces the code size and increases the performance. It provides two types of kernel mode. First, the nano kernel. It provides the fiber services which are non-preemptive. The second being the microkernel, which is a superclass or superset of nanokernel. This provides both task as well as fiber services. The Gpio chip driver structure. In Galileo, there are three types of Gpio chips: the GIP controller, the Quark legacy Gpio, and the I/O expanders. In Zephyr, all of these drivers are being accessed through the common framework, which is the Gpio.h. The PCAL9535A is a driver for the I/O expander. The GPIO designware is the driver for the GIP controller, and the GPIO SEH is the one to access the Quark legacy Gpio chip. The main program or the application calls the wrapper Gpio functions, which are defined in the Zephyr include Gpio.h, which indirectly calls the driver specific functions. Since there are various Gpio chips in the Galileo board, Gpio.h file defines a set of function pointers to access the internal operations of the driver. The PCAL9535A chip driver. This chip is a low-voltage 16-bit I/O expander that provides additional set of GPIO pins. This chip is bound to the I2C through the following master addresses. This table also defines the Zephyr device configuration name of each of the chip and provides the corresponding slave addresses. The device initialization of Gpio PCAL9535A happens after the device initialization of the I2C driver. Even though the level of initialization of both these devices is defined to be secondary, the configuration of the initialization priority of the I2C driver is higher than that of the PCAL initialization priority. This device has to be bound to the I2C master and hence uses the device get binding function. This function is used to retrieve the device structure of the low-level I2C device. I have provided the API structure defined in the driver. A few of these functions are like the config, read, write, callback, resume, and suspend. Let us look at a few of these operations. First, the write operation. Write operation is used to write the value to the particular pin or the port. Since it is binded to the I2C interface, the communication is via the I2C write function. I have provided the flow of the functions when GPIO pin write is being called from the application. It ultimately calls the GPIO PCAL9535A write in the driver, which communicates with the pin or the port through I2C write. Similar to the write operation, the read operation also functions with the I2C transfer operation. It reads the data or the value from the pin or the particular port. In configuration operation, we define the polarity, the direction, the pull up or the pull down value of the pin or the port. This is by setting up a certain GPIO flags. A few of the flags are the GPIO direction input, GPIO direction output, and if you set the flags to be as an interrupt pin, then you set flags such as the GPIO interrupt active low or active high, or triggering an interrupt on level or edge. GPIO callback operation. The GPIO callback handler defines the callback handler function. The following are its arguments. First, the port is the device structure of the GPIO device. The pin specifies the mask of pins that trigger the callback handler. The GPIO callback structure pointer, if initialized in or stored in the private data structure, when we use a container of macro, we can retrieve that private data structure of the device. We can initialize the callback handler by the GPIO init callback function. This is used to register and initialize the callback functions by setting up the handler and the pin mask. If the pin mask is set to 0, then the callback is never being called. We can allocate many callback functions in a program, but all of them should have the should be accessed via unique pointers. Moreover, the callback structures are not to be defined in the stack, as the interrupt needs to access the callback structures and does not access the stack of the current kernel task, since interrupt happens in its own interrupt context and has its own stack. The callback functions are being enabled by the GPIO pin enable callback function. This is by setting up certain flags for triggering an interrupt. In the GPIO PCAL 9535A driver, we see that none of the pins are being configured as interrupts, so they do not receive or trigger an interrupt. Hence, in this function, no operation is being performed. And we see that the arguments are being unused, and it returns a device invalid operation. Whereas in the GPIO DW driver, the enable callback function, it checks if the if the pins are being accessed or the entire port is being accessed. In that case, the callback is being enabled for the particular bit by setting the bit mask, or the callback is being enabled for the entire port. On an interrupt, the interrupt handler is being executed. In the GPIO DW ISR, it is checked if the interrupt status are being checked, and if the callback is being enabled, the IRQ, it invokes all the callback operations for the particular pins. Since there are limited lines available on every SoC, idealistically one IRQ line can only serve one device. It means that the number of devices that communicate with the processor is being limited to the number of IRQ pins. So we use the concept of shared IRQ, which allows multiple devices to be connected to the processor, and access allows multiple interrupt handler. GPIO has the pin 18, which is configured as the physical IRQ pin. Unlike Linux, which uses a virtual IRQ number, Zephyr uses this physical IRQ number. So that's all. Thank you for watching.